So let's try to make the algebra a little bit easier for most of these reactions. So in order to do that, what we have is we have what we call simplifying assumptions based on the actual chemistry that's going on. So let's say a reaction has a really large K. Well, if you've got a really large K and the reaction is A going to product B, large K, large, means that however much reactant you start with, that reaction is going pretty much all the way to completion, to the right. Now, if there's equilibrium here, you're going to have some small amount of reactant left, but it's so tiny you may not even be able to measure it. We've actually talked about that before. So if this is the case, if I have a large K, I can treat this reactant concentration as if it is completely disappearing and that it all goes to product. It's a limiting reactant type of reaction. So if I had more than one reactant and a large K, the limiting reactant would be the smallest amount of that reactant. All right? So what about if I have a reaction that has a relatively small K? So let's change this. Let's say that I've got a really small K. So if I've got a small K, okay, so I'm just going to draw a really small K. Now, remember how we calculate K? K is equal to products over reactant concentration. So if we have a small K, that means that the reactant concentration is really large and the product concentration is really small. There's not going to be a whole lot of product here, so we can say, yeah, goes in that direction, but it doesn't go very far. That means this is a big value down here. So when we calculate X under that set of circumstances, so the amount of X that disappears from this reactant, it may be possible to ignore that X with respect to that large concentration of reactant at equilibrium because this value is so small as to be insignificant. Okay, so that is one of the things that we're going to examine. So if a reaction has a relatively small K and a relatively large initial reactant concentration, the concentration change of the reactant, the minus X, may be neglected in that particular case. What we do is we follow the 5% rule. So you go ahead and you calculate X, and then you divide by the original initial reactant concentration, multiply times 100. Now, if that number is less than 5%, then we can ignore the X that is with respect to the reactant concentration, all right? So that's the protocol we're going to use. So the change should be less than 5% of the initial concentration of our reactant. Calculate this dividing the change by the initial after you finish, which we just did. Okay. All right, so here is our first example. Example problem with a small K. So here's our equilibrium constant. Now notice it's 10 to the minus 4. And so this would be 0.0000834. That's a really small equilibrium constant. So if I've got a relatively large initial concentration of my reactant, phosgene, ugly stuff. And why are these arrows down here? I'll try and fix that later. They should be up here. I missed a step. No worries, okay? All right, so at any rate, This is the change here is going to be minus x. The change here will be plus x, and the change here will be plus x. And then we simply add the initial to the change, just like we had before. 0.500 minus x. 0 plus x is x. 0 plus x is x. Now, first things first. X is not 0. There is some product over here. This is not a 0 equilibrium constant. We would have no reaction if it were a 0 equilibrium constant. Some of our reactant has moved to form products, but not very much. This change with respect to this concentration is very, very small. So that means that this x is so small that we can ignore it. Now we have to check afterwards to make sure that it is less than the 5%. The issue here is once we get to equilibrium, that if we round the equilibrium concentration of our reactant phosgene, it's going to be pretty close to what we started with, because this is so small, it's not really making a difference. Now, how do you make that estimation? Well, a good rule of thumb is look at your concentration of your reactant. It's 5 times 10. So if I were to write this as a scientific notation, it'd be 5 times 10 to the minus 1. This is 10 to the minus 4. There is a 1,000-fold difference between this fairly large concentration and this relatively small equilibrium constant. So the equilibrium constant, K, is 1,000 times smaller than our initial concentration, okay? Initial concentration of our reactant, okay? So in that particular case, we're going to go ahead and we're going to ignore that x, and that's going to make our math simpler. Okay, let's go ahead and work this problem. We'll build our ICE table here, ICE. This concentration is 0.500. This concentration initially starts at 0. We've got an equilibrium constant of 8.34 times 10 to the minus 4. We already suspect that this may be a small k, that we can ignore x with respect to the reactant concentration. So that's going to be minus x. This will be plus x. These are the changes. We're making a little bit of our products. And then we have 0.500 minus x. 0 plus x is x. 0 plus x is x. So let's go ahead and put the equilibrium constant expression together. Let's not ignore the x, and let's see what we would have to do. So we've got K is equal to our product concentration, which is CO, carbon monoxide. It's a nasty reaction, folks. Chlorine gas, also nasty. And divided by this phosgene stuff, which is terrible stuff, poison gas. And here we go. Let's go ahead and plug our values in. So I would have 8.34 times 10 to the minus 4 is equal to x squared divided by 0.500 minus x. All right, let's go ahead and let's solve this. So I'm going to multiply 0.5 times minus x times both sides. So 0.5 minus x, it cancels here. I'm also multiplying 0.5 minus x on this side. So let's go ahead and do that. So that's going to give me 4.17 times 10 to the minus 4, and that will be minus 8.34 times 10 to the minus 4x, because all I did was distribute 0.5 times, or distribute 34 times 10 to the minus 4 through the parentheses, and that will give me x squared. All right, and then I'll move everything over here on one side of the equation. I'm going to add this 8.34 times 10 to the minus 4, and I'm going to subtract 4.17 times 10 to the minus 4. When I do that, I wind up with, guess what? A quadratic equation. 8.34 times 10 to the minus 4x minus 4.17 times 10 to the minus 4. And that is, ladies and gentlemen, a quadratic equation. And now, in order to solve that, I'm going to need to use the quadratic formula. So I went ahead and I used the quadratic formula, which is minus b plus or minus the square root of b squared minus 4ac, and all divided by 2 times a. And when I did that, I got an x value of 0.0200. All right, so that is my x value using the quadratic formula. Let's go ahead and let's make a simplifying assumption here. Let's make the simplifying assumption that this x is less than 5% of this starting amount. Okay, we're just going to say it's small enough to ignore. Okay, so now let's put together, using this protocol, what our, this is the equilibrium constant expression. What's our k expression look like now, plugging in those values? Well, it's going to be 8.34 times 10 to the minus 4 is equal to x times x, that's x squared, divided by 0.500. Okay, and we're going to solve for x, so we multiply both sides by 0.5. So we'll do the same thing here. So that's just multiplying 0.5 times 8.314. And then we're going to take the square root of that whole thing. Well, let's just go ahead and... So that's going to give me 4.17 times 10 to the minus 4 is equal to x squared. I take the square root, and when I solve that for x, I get x is equal to 0.0204. So the difference here between my x's is in the 10,000ths place to a factor of 4. Let's go ahead and calculate the percent ionization, or follow our 5% rule. So that's going to be x, whatever x it is, over our starting concentration of COCl times 100. So that's what we're doing here. So that's going to be our percent is going to equal 0.0200 divided by our starting concentration. That's 0.500 times 100, and we get right on the nose 4%. So that's certainly cool. Now, if we do the same thing over here, we have an x value of 0.02, so that'll be 0. So we're going to calculate the percent. That'll be 0.0204 divided by 0.500 times 100. And when I do that, divided by 0.5 times 100, I get 4.1%. Okay, 4.1%. It's actually 4.08%. So only a 0.1% difference, well under the 5% rule. So whenever you have an equilibrium constant that's small relative to a fairly large starting concentration, that is, this is 1,000 times smaller than your starting concentration, my suggestion is go ahead and assume that's small and ignore it. That makes the math a lot faster. If you're doing that, if you have a problem like that, here's the nature of x. X will simply be equal to the square root of k times your starting concentration. Okay, that's the nature of this particular beast. Okay, and that'll just give you the answer. What about a simplifying assumption when you have a really large K? So here is arguably an enormous equilibrium constant, 10 to the 52. What this is telling you is that this reaction is going to go all the way to products effectively. There may be some of your reactant concentration left, but it'll be so small that it's probably undetectable. So this is a huge K going all the way to the right. Now, some of them may not be that large, but this one certainly is. But large K, all the way to the right. So our change here is minus x. Our change here is plus x, and at equilibrium we have 4.0 minus x, and 0 plus x is just x. What we're saying is assume that the reaction goes to completion. That means that all your reactant gets used up and all you have is product. So let's make a prediction. Since my reactant concentration initially is 4, if it goes to completion, that means that my product concentration at the end of it should also be 4. And this concentration should be unmeasurable to any reasonable degree of instrumentation that permits me to measure really small concentrations. Certainly in a wet chemistry lab, not something you'd be particularly concerned with. By the way, why haven't I included in this equilibrium S8? Well, hopefully you picked that out because S8 is a solid, and solids don't change in concentration, so they don't get included in the equilibrium constant expression. The solid has to be there. You're not going to get any SO2 unless you've got some sulfur, but it doesn't change in concentration, so we don't include it. All we have in the equilibrium constant expression are oxygen and sulfur dioxide. So let's solve the problem and validate our prediction. So here is our reaction. We've got I, C, E. And we're not going to worry about this because, again, it's a solid and we don't include those. But this is 4 molar or 4 atmospheres. It's some unit of pressure. We could still say 4 molar. It doesn't really make a difference at this point. The change is going to be, because the coefficient is 1, the change is minus x, the coefficient is 1, the change is plus x. And down here we're going to have 4.0 minus x, and then 0 plus x is simply x. Let's set up our equilibrium constant expression. I'll do it over here. K is equal to SO2 divided by O2. Now I'm just going to plug in my values. So my K value is 4.2 times 10 to the 52. That's going to be equal to X divided by 4.0 minus X. Now I certainly can't ignore this X because this X is huge. Okay, it's huge. But I'm going to go ahead and solve the problem. So I will go ahead and multiply both sides by 4 minus X. Okay, over here it will cancel. I'm going to do the same thing over here times 4 minus X. And when I do that, I get over here 4 times 4.2, that's going to be 1.68 times 10 to the 53, and that will be minus 4.2 times 10 to the 52x equals X. Now let's combine our terms, and we're going to combine our terms by adding 4.2 times 10 to the 52x to both sides. So over here, the same thing, 4.2 times 10 to the 52x. All right. So I think everybody sees over here, the 4.2 times 10 to the 52x goes away. What do you think is going to happen when I add 1x to 4.2 times 10 to the 52x? Well, to any reasonable number of significant figures, it's just going to equal 4.2 times 10 to the 52x. Doesn't equal 5.2. Don't add 1 to 4.2, you're adding it to 10 to the 52. So that extra x you've added, it is way the heck down here. It is off the page. I'd have to write 52 of them out before I added another x in there. So that's just going to equal 4.2 times 10 to the 52x. So that gives me 1.68 times 10 to the 53 is equal 4.2 times 10 to the 52x. And I'm going to solve for x by dividing both sides by 4.2 times 10 to the 52. It will cancel here. And when I divide this, it's going to be divided by 4.2 times 10 to the 52. What I get is x is equal to 4 to any reasonable number of significant figures. Now, the truth is, x is actually equal to something like 3.99999, but I would have to go out to 52 places for that last 9. And then my starting concentration, while it is effectively 0, after subtracting 4 from 4, it's effectively 0. In reality, my O2 concentration could be described as 0.000000, and I would have to, again, go out to those 52 decimal places in order to get to a single non-zero digit. Okay? All right, hopefully you understand that. Bottom line, if you have a really large K, assume the reaction goes all the way to products. So using simplifying assumptions, what equation should be solved in order to calculate the concentration of H plus when 0.5 molar acetic acid, this is a weak acid, we're going to be covering those extensively in the next chapter, is allowed to dissociate. Now we've got a relatively small K value, 10 to the minus 5. Let's compare it to our starting concentration. It's 0.5. 0.5. So the question is this K value 1,000 times smaller than this starting concentration? If it is, okay, if it's 1,000 times smaller, okay, simplify using the protocol. If you can't remember what it is, go back to the first simplifying assumption, okay? All right, I think we're almost done. Here's our summary strategy for calculating equilibrium concentrations. Write a balanced chemical equation. Construct an ICE table, initial change equilibrium concentration. Fill the table up with the known information, all your concentrations, where the change is going to be. Now, if you have non-zero concentrations initially for everything, you have to calculate Q to determine whether reaction goes forward. Q is less than K, reaction goes forward, or reverse, Q is greater than K. So go back and watch the video on calculating Q, or just on the reaction quotient, to remember how to do that if you've forgotten already, all right? Complete the ICE table in terms of the variable X. Simplify if you can. Okay, write an expression for K based on the balanced chemical reaction, and then substitute the equilibrium line. That's the last line from your ICE table into the expression for K. My suggestion is always to write the equilibrium constant expression in the symbols for the components of the reaction, and then plug in the values from your ICE table. Okay, solve for X, and then answer the question as described. All right, I think that's enough.